Imagine your robot is stuck in a dusty library. It can't step outside and it can't try anything new, and all it has is a stack of old receipts, as a paper trail of everything some robot did months ago. But here's the trap. When the model looks at its options, it's naturally going to hunt for the biggest payoff. But that peak that it sees is often in a blind spot, is a part of the map that the data never actually covered. And this is where things can become a problem, as the model doesn't need to be broken or evil to fail, it just needs to be confidently wrong about a place that it's never been. Offline RL sounds simple at first. You already have a data set and you already have rewards. So why not just run Q-Learning and improve the policy? But that's because Q-Learning has one aspect that becomes very dangerous offline, and that's the max. At a state, the data set only contains a few actions. The actions are the bright dots. Everything else is gray because the data never went there. A neural Q function still has to give values to the gray region because it's a function approximator. So when a Bellman target says take the max over the next actions, the max does not care what was in the dataset, it scans everything. So if there's a fake spike in the gray zone, the max points out like it's found treasure, but there's no evidence of that being the max. This is why behavior cloning starts to look pretty appealing, as behavior cloning basically says, don't go searching through actions you've never seen and just copy what's in the dataset. And honestly, it does help as it keeps the policy close to real actions from the data instead of wandering off in some unsupported part of the action space. But there's a catch. The dataset is not perfect. It has good actions, but also has boring, messy, and sometimes just bad actions. So if we copy the data, we stay safe, but we don't really get much better. We want something to improve on the policy without making up actions the dataset never supports. And that's the idea behind implicit Q-learning. The key object is the expectile. If we look at one state, on this axis, every blue dot is an action from the replay buffer, and the height of the dot corresponds to the current Q estimate. Low dots look bad and high dots look promising. So let's place a horizontal marker V of S among the Q values. If tau is 1/2, the marker behaves like a mean, and the high points and low points pull on it with equal strength. So V sits in the middle of the dataset. But IQL doesn't want the average action. It wants a value that leans towards the better actions of the dataset without leaving the data. So that's what the asymmetric squared loss does. When a Q value is above V, the residual is positive, and with tau being above 1/2, the positive residuals get a stronger weight. That means the higher dots pull harder, and the low dots, they still matter, but they pull with much less force. So as tau rises, you can watch as the value line slides upwards, and it's not jumping to a random spike in the void. Instead, among the actions that we have, that we actually saw, it finds the greater than average looking values. And that's the expectile lens. It acts like a softmax function over the values we actually saw. Now that the lens gives us V, the backup is safer. So in regular Q-learning, we look at the next day and ask, what's the best action we can take from here? But that means checking every possible action. And that's where things can go wrong, as the max value can jump into areas that we really don't have data. IQL is able to avoid that, because instead of using another max, it uses the V value, which we already learned from the previous state. And the target becomes reward plus gamma times V of next state. So the reward still flows backwards, and IQL is able to learn from the future. The difference is that it only learns through transitions we actually saw. So one recorded path can take us to the middle, and another path can take us from the middle to the reward. If they connect, IQL is able to stitch them together. But if there's a gap and the screen says no data, that means IQL does not invent a shortcut. Now we still need a policy. On screen, the blue dots are the dataset actions the actor is allowed to copy. The yellow line is V, our baseline, and for each dot, we compare Q to that value. A equals Q minus V. If a dot is above the baseline, the action did better than expected, and if it's below, it did worse. The purple curve we saw is plain behavior cloning. It copies the dataset as is, and IQL is able to bend that curve, and when the green weighted line appears, the good dots swell and pull the policy towards them. That is advantage weighted cloning. The actor is still learning from real actions on the screen, it's just copying the greater policies better. These four cards are the knobs. Tau low means the lens stays too close to the average, so improvement is timid. Tau high means the lens can get baited by noisy samples. Beta big makes the weights too flat, so the actor barely changes, and beta tiny makes the actor pile onto too few actions. Then the bottom warning is the real limit is that there's no support means no magic. So if the dataset never recorded useful transitions, IQL cannot invent it. So the whole trick is these three boxes. First, the lens. It finds a high but supported value from the action the dataset actually shows. Second is the backup. It pushes the value backward through recorded transitions. And third is finally is the weighted copy. It turns the best supported actions into a policy. And notice the gray strip at the bottom. The void stays void. That means no explicit max over unseen actions. There's no pretend exploration, and it's just a lens, a backup, and a weighted copy. And that's how implicit Q-learning is able to learn without inventing actions. Thank you for watching.